Okay, so again, sorry for the quality of the sound on this video. I'm just going to be talking to my computer because once again, I forgot my headphones. Okay, I just wanted to go over this one that we're doing in class today, just so you have it for reference to see the kind of general process that you're going to follow. Okay, so first things first, I noticed a lot of you stumbled up today because you didn't draw a picture. Maybe in Physics 20 it was just an annoying thing we made you do for most questions, okay? Now it really will help you out. That's why we tried to instill that skill in you, okay? So a before picture and an after picture. So before, we have a center who is stationary. So VC equals 0, VC initial, right? And he's checked from the side by a 104 kilogram defenseman skating at 1.82 meters per second east. So the defenseman initial east. Now that's all in the x-axis, right? So let's consider our momentum now. Yes, that's his V, right? But also that means the momentum is that way. The momentum of the defenseman initial. Now, add up all the momentum. All we've got is this one, right? So that's our VAD. Overall, that's our VAD. What about in the x-axis? Let's look at the x-axis. Well, add them all up. It's just that one, right? So add that one. That is in the x-axis. We're going to define east as the x-axis. So if we add that, that is the total momentum in the x-axis initially. And finally, in the y-axis, add all the y components together. And yes, there's none. So there is nothing to add so that the resulting momentum in the y-axis is 0. Okay, so initially there's no momentum in the y-axis. Let's look now at after. Right away, if I just said there's no momentum initially in the y-axis, we know there can be no momentum finally in the y-axis. Okay, so any y momentum that appears in one of our objects must end up being canceled out by the y momentum of some other object. Okay, so let's start this. Let's read on. Okay, so the center is checked and bounces off at 0.940 meters per second at 18.5 degrees south of east. So now the center has some velocity that way, which right away, if we're going to end up with no y momentum, right? With no y momentum, this must have some upward component because this has a downward component, right? So his momentum is now something like that, which means to end up with no y component, right, this needs to be some up momentum. Because, right, this has an x component, looks like that. And it has a y component that looks like that. The same way this has an x component that looks like this. And a y component that looks like this. How do we know? Because of the law of conservation of momentum. All our VADs should look the same after, in terms of the result we get, okay? So our overall VAD, we know that our resultant needs to end up looking like this. But the center now has a momentum that looks like that. So how do we get back to a momentum that looks like this? Oh, because the other guys looks like that. So tip to tail, and then our resultant momentum, right? So we have P center final and momentum defenseman final gives us our resultant, our total final momentum, which of course looks exactly like our total initial momentum. See how that looks exactly like that? As it should, law of conservation of momentum, okay? But if that's going to be the same, then our x and our y also need to be the same. Momentum must be conserved in each axis, okay? So VAD in our x. Well, how do you get the x component, the resultant x component of anything? Add up the x components of all the vectors that make it up. So we have our final momentum made up of the center's x component final and the defenseman's x component final. So that looks like this. Going to be a little bit smaller, but then when we go to draw the resultant, the sum of the final momentum in the x is the same as the initial, because of course it was all in the x initially. Now in our final, yes, we have some upward momentum here in the y-axis, but we also had some downward momentum here. In fact, that's how we knew this guy had to go up, is because this guy was going down, and we knew that there was no momentum initially. So how do you draw no momentum? Well, you don't. You don't draw anything, right? Those cancel each other out. so that there is no y momentum finally, which we knew at the very beginning. Because there was none initially, so there better be none finally. Okay, now how do we actually go into analyzing this? Now let's just take a second to think about what we're looking for here, right? What's the point? We need the velocity of the defenseman immediately after the check. So we are looking for velocity of the defenseman final. That's what we want. We got to think now, how do we get that, right? What are all the pieces we need to get that? Well, look at our diagram. Okay, what are all the pieces we need? Yes, this is momentum, but his velocity is going to look similar, right? His velocity is going to look like that. Figure out how big that is. Since it's on an angle, it's not perfectly nicely in one of our axes. We're going to have to figure out its x component. We're going to have to figure out its y component. Okay? And then with Pythagorean, we can figure out what it is. And then with SOHCAHTOA, we can figure out theta. So just pause here and realize, hey, this is what you've been doing in Physics 20. You did this a lot in Physics 20, right? Now we're just doing it with momenta as our vector instead of a force or something, okay? So there's our game plan. We need to get its x component. We need to get its y component so that we can put it together with Pythagorean to get the overall BDF, okay? And all we're going to do to get the components is apply the law of conservation of momentum, okay? Momentum must be conserved in the y. That will let us figure out how fast he has to be moving, according to our diagram here. Momentum must be conserved in the x. That will allow us to figure it out here, so that will allow us to get v eventually. So there's our game plan. We're going to get x, we're going to get y. Let's do it. You have a couple options, but let's start with the y-axis, okay? Because we kind of know right away there's some more zeros going on in the y-axis. That means it will be nicer to deal with. So all of the momentum initially in the y-axis is equal to all of the momentum finally in the y-axis. Now, just like always, all the momentum initially in the y-axis is the y component of the momentum initially for every object. So this guy's initial y component of his momentum. This guy's initial y component of his momentum. So add it up. We've got P of the defenseman initial in the y-axis plus the momentum of the center initially in the y-axis is equal to, well, now they're moving off separately, but they still must have the same. So all the y components after. So P of the defenseman final in the y-axis plus the momentum of the center final in the y-axis. Okay, now here's what's nice. From our diagram, right, draw the diagram and think about it, it's all in the x-axis. So even though the defenseman has some momentum, he doesn't have any in the y-axis, so that's 0. Of course, the center doesn't have any momentum in the y-axis. He's not even moving, okay? And then look at this. Remember what I always say, let the math tell you what you know to be physically true. That's a good feeling when it checks out with your intuition about the problem. You're saying that 0 is equal to the total final momentum in the y-axis. Hey, that's exactly what we started out saying. We said the total initial momentum in the y-axis was 0, and so therefore the total momentum final in the y-axis would be 0. And look at that. That's what our math has led us to now. Okay, we care about the velocity of the defenseman, so let's just isolate. And look at that. Another thing that we knew had to be true. What did we say? We said if this guy's going to have some momentum down, the other guy better have the same amount of momentum, but up. In other words, equal, but in opposite directions. Hey, mathematically, that's exactly what this is saying. Equal, but in opposite directions with opposite signs. Okay, now let's actually turn this into variables we know. Momentum of the defenseman final will, of course, be the mass of the defenseman times his final velocity, the y component, right, is equal to momentum final of the center in the y-axis will be the mass of the center. Every p is an mv. So v, c, f, y, right? Which velocity? Whoops, negative. Okay, every p is an mv. It's just a matter of which m and which v. If you want p, c, f, y, you need v, c, f, y. Now, the whole point of this was to find the velocity, the final velocity of the defenseman. So let's go ahead and divide both sides by the mass of the defenseman. And we have that. There we go. Okay. The only issue is we don't know this right away, but we can find it pretty easily, right? Because we know the final velocity of the center. It's given to us in magnitude and direction, 18.5 degrees south of east. So south of east, this is 18.5 degrees. This is its x component. This is its y component, right? We want VCFY, so opposite over hypotenuse, right? SOHCAHTOA, so sine of the theta equals opposite over hypotenuse. Therefore, all right, we've got VCF. We know it, so let's just go back here. Okay, we can sub that in. If you want to find VCFY, go ahead. I'm just going to sub in though and say that this therefore equals negative mass of the center, VCF. VCFY, as we just found, is VCF sine 18.5 degrees, the y component of the center's final velocity, divided by the mass of the defenseman, which equals negative 97 kilograms. Just plugging in now, VCF is negative 0.940 meters per second. Okay, now here's something you have to be super careful about. Why is it negative? Okay, because I decided to define north and east as positive and south and west as negative. Now, you've got to be careful here, right? That means VCFY is in the negative y direction. So it's on us to just kind of slap that negative on this and get that VCFY is going to end up being negative. You have to notice that. It's not just going to naturally happen in the math. There are a few times in physics where you have to be responsible for interpreting stuff. Okay, and so that is because VCFY is pointing down, which is our negative y-axis, we are going to put that in as a negative when we do it. So its y component is negative, okay? Its x component is still positive, right? Because we define that way on the x-axis as positive. However, its y component is defined as negative on our y-axis, so we're going to put in that negative there. Again, you just have to know that and put that in, okay? So just be careful on those. So I got that the y component of the defenseman's final velocity was meters per second. We got the positive. Good. We were expecting the positive, right? Because we defined south as negative. We knew they had to have opposite signs. So when we said the center is going south for its y component, and that's negative, we knew right away this one would have to be positive. The defenseman's would have to be positive. Okay? So got to be north, which we already knew, but doesn't hurt to have the math help us out there. Okay, now, we didn't want the y component of the defenseman's final velocity. We wanted the defenseman's final velocity overall, not just one axis of it. Okay, so now, how do we do it? We go to the other axis. So we just did the y-axis, now let's move over to the x, now that we have the y component. Okay, so now we have the y component, right? We're starting to construct this picture. Problem is, we don't know the angle, right? If we did know the angle, we'd be good, but we don't. So now we have this y component. If we can get the x component, well, there we go. Now we've built that triangle because we can figure out what the hypotenuse would be. If you have two sides of a right triangle, you can figure out the hypotenuse with Pythagorean theorem. So here we go. How do we get the x component? Like we just said we need to do, we're going to have to go to conservation of momentum in the x-axis. Like always, add up all your momentums before, all your momentums after, and then just solve for what you know. Are there going to be a lot of variables? Yes. But is it going to be any different than any other problem you've done where there's a whole bunch of stuff you know and one thing you don't? Nope, it's always going to be that. Okay? So we have the defenseman's initial x momentum plus the center's initial x momentum. And hey, that was 0 because the center wasn't moving. Is equal to their final x momentum. Okay? Just changing these p's into mv's. Right? And what we're after is the x component of the defenseman's final velocity. That's what we want. Okay, so we'll isolate for that. And divide by md. Now here we go. We're getting close. You can taste it. Okay, now the x component of the center's final velocity, remember, let's pop back up to our triangle, right? Here it is. The x component would be cos 18.5 times VCF, because adjacent over hypotenuse, right? Cos of 18.5 will equal VCFX over VCF. Manipulating that, you'll get that. So really what we're saying here, okay, is equal to that, which, let's plug in everything we know. Sorry, VDIX we knew, the question just told us, right? Because it was only, VDI was only in the x-axis, so VDIX is VDI. Be careful paying attention to signs. Remember our convention. We made those positive, those negative. Okay, but he was going to the right, so that is correct in being positive. All divided by 104 kilograms. So I got that the x component of the defenseman's final velocity was that. Okay? Why east? Because I got a positive answer. Technically, we didn't actually 100% know that, right? It's possible that he was going west and this was just so great as to overcome that, but we got a positive, so it will be east, which feels right. It probably should be, okay? So now, let's think about what we got here. We've got VDFX, so we've got VDFX to the east, right? We got VDFY in the last step, right, to the north. So look at that. Look what we got. We have enough information to get the resultant. The hypotenuse of that triangle is just the net vector. So we can get VDF. Okay? Don't forget it's a velocity, so it needs a direction too. In this case, that will be an angle. So, Pythagorean theorem. VDF squared equals, C squared equals A squared plus B squared, so equals VDFY squared plus its x component squared. So VDF is equal to the square root of what we just found, 0.98. We're so close, we're actually getting a number now for the defenseman's final velocity. It's going to be 1.03 meters per second. However, that is not a complete answer because it's a velocity and therefore it needs a magnitude and a direction. We've got the magnitude. So let's go back to our thing here. Okay, this helps us out quickly. Theta, the safest way is to go with tan just because there's more calculations between this and the beginning, the numbers they gave us, than there are these. Not much, but a little bit. So tan theta equals opposite over adjacent. Okay. Inverse, we want theta, not tan theta, so we take the tan theta of both sides. So we take the inverse tan of both sides, and then theta equals. Okay. We have those just written above. Now I get to 3 sig digs that theta is 15.7 degrees. Now, which way is this? It's either north or east that we're going to reference from, okay? The way we've drawn it, we started at east, and to make VDF, we went north of it, right? We went north of east. So the way we drew it would be north of east. You could have flipped this triangle and then gone east of north. That's just not how I set it up. Maybe you set it up a different way, okay? The east of north way, which would just be 90 minus 15.7. Okay, so now we put in that angle, and we will be done this question. Okay, is it a longer process than what you did in Physics 20? Yes. Is it anything more difficult? Honestly, not really, right? It's just about knowing the fact that momentum must be conserved in the x and in the y. More variables involved? Sure. But is anything different where we just don't know one thing and we know everything else? Not really. It's the exact same in that regard. Okay? So draw your pictures. They help realize what's going on in the first place. Okay, have a great weekend.